In this video, we are going to see the definition of the space of square integrable functions. This space is all important in the study of Fourier analysis. We will not study much about Fourier analysis in this course, but what we are about to do in this video will definitely serve as good motivation for the study of Fourier analysis in a future course. So the definition of square integrable function is sort of an illustration of a statement that I keep making, that mathematicians are not very creative when it comes to naming stuff. Let f be a function from I to r such that f squared is in L of I. Then we say f is square integrable. So those functions whose square are integrable are called square integrable functions. The collection of all square integrable functions is denoted by L squared I, or L2 of I more commonly. Now, first of all, let me make a remark. It is neither true that L of I is a subset of L2 of I, nor is it true that L2 of I is a subset of L of I. Neither of these statements are true. So to see this, consider the function x power minus half on the interval 0, 1. Okay, you can check that this function is going to be in L of I, but the square of this function, which is just 1 by x, this is not in L of I. Okay, so this function x power minus half is not an element of L2 of I. Its square is not integrable. On the other hand, if you consider the function 1 by x on plus 1 infinity, okay, then this function is not Lebesgue integrable, as you can check. Is not Lebesgue integrable, but 1 by x squared is in L of 1 infinity. So neither containment that you expect is not going to hold true. However, we can write a sort of a trivial proposition which sort of gives one common criteria for checking whether a function is square integrable. Suppose f from I to r is Lebesgue integrable and bounded almost everywhere. Then f squared is Lebesgue integrable, or in other words f is an element of L2 of I. So if you have a function that's both Lebesgue integrable and almost everywhere bounded above, then it's going to be Lebesgue integrable. The square is going to be Lebesgue integrable. Well, the proof is really nothing. Well, consider mod f squared. Well, this mod f squared is going to be less than or equal to m times mod f, where m is the bound. Of course, this is true almost everywhere. Okay, so this means that the function f squared, which is of course measurable because f is a measurable function being Lebesgue integrable, and modulus of f squared is bounded above almost everywhere by a Lebesgue integrable function, namely m times mod f. By a Lebesgue integral function, it follows from earlier results that f squared is Lebesgue integrable as claimed. So this is one really simple and stupid criteria to check whether a function is Lebesgue integrable, square integrable. Now another natural question that crops up is, what type of space is the space of square integrable functions? Well, thankfully it's a vector space, which is the essential content of the next theorem. If f, g are in L2 of I, then so is AF plus BG, where A and B are any real numbers. This is essentially showing that the space of Lebesgue square integrable functions is actually going to be a vector space. Proof. Well, what is AF plus BG the whole squared? Well, this is nothing but a squared f squared plus 2abfg plus b squared g squared. Okay, now we already know that a squared f squared and b squared g squared are Lebesgue integrable, simply because f and g are assumed to be square integrable. What about this middle term fg? Is this also going to be Lebesgue integrable? Is that clear? Well, observe that mod fg is going to be less than or equal to f squared plus g squared by 2. Okay, this just follows from observing that f minus g the whole squared is greater than or equal to 0, and f plus g the whole squared is also greater than or equal to 0. From that it follows immediately that mod fg is less than or equal to f squared plus g squared by 2. But this is Lebesgue integrable simply because f squared and g squared are, therefore f squared plus g squared is, and f squared plus g squared by 2 is also Lebesgue integrable. So fg is a measurable function which is bounded above by a Lebesgue integrable function. Therefore, by an earlier result, fg will be Lebesgue integrable. It follows that AF plus BG the whole squared is also Lebesgue integrable. So as a corollary of this simple observation, we get that the space L2I is a vector subspace of the space of functions from I to R. So the space of square integrable functions is going to form a vector subspace. Now we can define a norm on this space L2I. Well, what is this norm? Definition: norm on L2I. If f, g are in L2I, then define the inner product of f and g to be just by definition integral over I of fg. This makes sense because we just saw in the previous proposition that if f and g are square integrable, then the product is going to be Lebesgue integrable. Therefore, this definition makes sense. Now that you have an inner product, the norm is automatic. So norm of a function f would be by definition integral of f squared I whole power half. Okay. Now that this thing is an inner product is left as an exercise for you. There is really nothing much to prove. Show that the inner product we have defined is indeed an inner product on L2 of I. Only one property will fail, so let me put a star. Because this is not going to be entirely satisfying all the properties of an inner product. One caveat which you will have to think over: it is possible for inner product f comma f to be equal to 0 even if f is not equal to 0. The reason is, if you have a function which is 0 almost everywhere, then that function is automatically going to be in L of I, as we have remarked in earlier videos, and the integral is going to be 0. So functions that are not identically 0 could have 0 norm under this inner product and norm. So what is essentially going to happen is that under this norm, in quotes, L2I is a semi-normed vector space. So something that satisfies all the properties of a norm except for the fact that if the norm is 0, the function is 0, that is known as a semi-normed vector space. Now one thing that I must remark, which is sort of a somewhat advanced remark at this stage, is that this is not really an issue. This is not an issue. After all, from the perspective of integration theory, two functions that are almost everywhere equal are indistinguishable because their integrals are also equal. So what we can do is we can put a relation on L2I declaring two functions that are almost everywhere equal to be related, and then we can define the equivalence classes. So equivalence classes will consist of functions which are pairwise almost everywhere equal. We can define the equivalence classes to be the functions, because from the perspective of the Lebesgue integral, functions that are almost everywhere defined and almost everywhere equal to other functions should be identified, because the Lebesgue integral is blind to almost everywhere differences. The Lebesgue integral is blind to differences on sets of measure 0. So two functions that are almost everywhere equal will behave exactly the same from the perspective of the Lebesgue integral. So what you do is you declare any two functions that are almost everywhere equal to be the same. You do that formally by setting up an equivalence relation. On this set of equivalence classes, we get a norm, not just a semi-norm. Okay, so for many technical purposes, many authors identify functions that are almost everywhere equal and study that space instead. Now there are some annoying technical issues that will crop up if you go this route. For instance, if you just take a continuous function, that makes no sense anymore, because this function is part of an equivalence class, and that equivalence class has functions that are completely discontinuous everywhere. Okay, so recall that the indicator function of the rationals is not continuous, it's discontinuous everywhere, but it is almost everywhere equal to 0. Therefore, the 0 function, which is as nice and as continuous as possible, is in this perspective equal to the characteristic function of the rational numbers, which is everywhere discontinuous. So this sort of annoying technicalities can prop up, but that's part of life. Okay, so one final remark, if you don't go this route, what you end up is the space L2I is a symmetric space. What I mean by that is the definition D of Fg by definition equal to norm F minus G will give a function that satisfies all the properties of a metric space, of a metric, except that dfg could be equal to 0 even if f is not equal to g. If f and g just agree almost everywhere, still the distance between f and g will be 0. So this is what is known as a semi-metric space. Of course, to check that it is a semi-metric space, you can just appeal to the abstract results that we have shown, that once you have an inner product, you have a norm, and once you have a norm, you have a metric. This was all done way back in the beginning of this course when we did a detailed study of metric spaces and normed vector spaces and inner product spaces. Okay, so all the properties of the normed spaces will continue to hold except for this one caveat. Let me just summarize the various properties that will hold, and I'm not going to provide a proof because we have already proved it once when we studied the theory of metric spaces and normed vector spaces. If f, g and h are in L2 of I and c is a real number, then we have these properties. We have inner product fg is inner product gf. This you have to prove when you show that f, the inner product we defined is indeed an inner product, you would show this as a part of that, but really there is nothing to show. It's just because integral fg is same as integral gf. There's really nothing to show. And then you have integral of f plus g comma h is just integral f h plus integral g h. This is again part of the proof that this is going to be an inner product. Again, there's really nothing to show. This just says that integral of f into g plus h is integral fg plus integral fh, which is just immediate from the properties of the Lebesgue integral. And 3 is this scalar thing, integral cf comma g is c times integral f comma g. Again, straightforward, trivial to show. And then you get the properties of the norm, which we have already shown once when we studied normed vector spaces. Norm cf is norm c, absolute value of c times norm of f. And then we have the famous Cauchy-Schwarz inequality, which says that absolute value of inner product of fg is less than or equal to norm f norm g. This will follow from the abstract Cauchy-Schwarz inequality we proved long back. And finally, a consequence of the Cauchy-Schwarz inequality, which is the triangle inequality. Norm of f plus g is less than or equal to norm f plus norm g. So this is just a summary of the properties enjoyed by this norm on this semi-normed vector space L2 of I. In next week's videos, we will see some convergence theorems on L2 of I and also show that L2 of I is a complete space. This is a course on real analysis, and you have just watched the video on square integrable functions.